I want to talk about the kind of reconstruction of a measure from its moments in a general setting. And so I want to consider a general category, which you can think of as being the category of finite groups. Or maybe we can take finite groups with some extra structure. Or maybe some well, there'll be other examples, but let me just start with those two. And I want to consider measures on the set of small or set of isomorphism classes of small pro objects of C. And then I have this notion of a moments.
Small means that one to every element of C is finite.
Good question. Almost. If every morphism in the category factors as an epimorphism closed with a monomorphism, that's what I mean. If that's not true, I mean something slightly different. So maybe we should just assume that every morphism factors as an epimorphism closed with a monomorphism, and then yes, small just means finite harms to every object.
Factors in unique way, or?
I think uniquely is the assumption that I need. I'm not 100%.
But in category theory, they also have strict. It's only that this kind of factorization is sometimes it's convenient to have kind of strict epimorphism. I mean, there are different conditions related to the notion of epimorphism and monomorphism. So this kind of I mean, when you really want to have unicity of the factorization, which also in some usual categories like sets or groups or abelian categories.
You mean effective epimorphism than monomorphism?
What?
I mean, what you call strict epimorphism, I think it's usually called effective.
Well, there are different books and so on. I mean, so either all the monomorphism set. So you want to anyway. It's so you probably mean one of those conditions that.
Okay, but for real life example, you think of like this category has space for functional of sets, finite sets, maybe, yeah.
Yeah. Well, most of the cases that I'm considering. I mean, sure you can rig something up in all the cases I'm considering.
So you assume that the automorphism of any object is finite in particular.
Yeah. I will make some general statement, and then I'll put some actual hypotheses on my category, and that will be one of them. Are they determined by their moments, which are given by this formula, the integral of the number of surjections from x to g, d mu of x, this is like our, maybe the integral, I should say integral over x and prof against, Sarah said you shouldn't write d mu, you should just write mu. So it makes sense, so because we're thinking of groups as the prototypical example, we decided to just use group notation for elements of the category, so we'll call them something like G or H or K, or a name that would be common for a group. So yeah, so the sigma algebra for the sigma algebra generated by like the set of x such that G is a quotient of x. So there exists, or maybe we'll be more precise, there exists a surjection from x to G. Like, you know, kind of the minimal thing in algebra you need to make this function continuous. I mean, it's not obvious that the function will be continuous on the sigma algebra. And so we had written down a kind of an argument giving criteria for a measure to be uniquely determined by its moments, as well as giving, showing a measure, you know, criteria for a measure to exist, and an actual formula for the measure in the category of groups. And so then we need to figure out, like, what assumptions on the category are we using here? What is the widest class of categories in which this argument works? And it was slightly subtle to find, because I think it's not, the criterion we have is like not a purely category theoretic description, because the sort of, for a lot of the argument, we're not looking at the full structure of the category. So what I mean by that, we're only looking at surjections, or the epimorphisms in the category. So because we want to count these moments via moments in terms of epimorphisms, it makes sense to define the topology in terms of epimorphisms, and then really only the epimorphisms of the category ever play a role. So in fact, I mean, what I could do, I'm not going to do it because it would be a very weird assumption. I could make the assumption that every morphism in the category is an epimorphism. But it's, I mean, for practical examples like groups, it's more convenient to say we have an existing category which is not every morphism and epimorphism, we just only consider the epimorphisms. And so so a completely general statement, if you have an object G in any category, all the epimorphisms, or maybe a small category, isms from G to H up to isomorphism form a partially ordered set. So for any H, so for all the set of all, for all H, all epimorphisms G to H form a partially ordered set, where like the largest one is the identity G to G, and if you have a factorization G maps to H1 to H2, then we're thinking of G going to H1 as being larger than G to H2. And the key assumption we need for the argument is that the quotients of any object form a finite modular lattice. I will explain it because I explain that next. Okay, so let me explain what each word means. Okay, so finite is easy to mean the finite as a set. So lattice is a partially ordered set That's a poset where any two elements x and y always have a greatest upper bound which I write using like a union kind of symbol and a least upper bound and a greatest lower bound.
Do you assume in the lat, it depends on now on the reference, that there is a minimal and maximal, that there is a smallest and largest element?
If it's finite, then
Yes, if it's a finite, then there must be a minimal and maximal element. So,
unless it is empty, in which case.
But this lattice is not empty because it always contains the identity element. Yeah, some lattices maybe. And so the modular lattice, the most compact way of writing it is the modular law, which says that if A is less or equal to B, that implies that A union x intersects B is equal to union x intersects B. So it's probably easiest to convince yourself this is true for the lattice of subsets of a set where this symbol represents union and this represents intersection. However, I don't think it's very enlightening what this what this means.
So actually, the lattice of subsets, as far as I remember, satisfies a stronger condition.
Yeah,
it's just distributive.
Exactly, yeah.
Which
So you
implies the modular condition, but it is stronger.
Correct. So my claim is just that you can check that. So I'm going to give examples of modular lattices, I guess. You can check this in those examples. I'm just saying that the sets example is the easiest to see why this is true.
So for living group, I mean, it's probably
No, submodulus of modulus of any group.
But it doesn't matter. I mean,
Yeah.
okay. So
Or normal subgroups of a group.
And normal subgroups.
Yes.
Okay.
Not subgroups of a group.
So those are all examples. I'm not disputing those are examples. My claim is just that it's easier to check that this equation is true for subsets of set. So yes. So okay. So yeah. But okay. Let me give the examples now, and then I'll say more. So examples. Normal subgroups of a group. So submodules of a module. Those both include, as special cases, subgroups of an abelian group, so I won't write that down. I will write subsets of a set, even though that makes people unhappy. And let's do ideals of a ring also.
It's invariant under passing to op as well, right?
Yeah, exactly. Yeah.
It is invariant under passing to op, and yeah, so that's what we're doing. Yes, so we decided it makes more sense to define the lattice of quotients or define the poset of quotients to respect the size relation. So larger quotients are larger elements of the poset, which means that the lattice of quotients of a group is going to be the dual to the lattice of normal subgroups. The lattice of quotients of a module is going to be dual to the lattice of submodules. And similarly for ideals in a ring, you get the dual lattice.
But you mentioned them 2 times. Right? Ideals for ring, because it's also moduli.
It's submodule for module. Yeah.
Oh, right. That's a good point. That's a very good point. Ideals are just submodules. They're not submodules with extra structure. They are just submodules. Okay. But yeah, so as categories, obviously the category of rings is different from category of module. So another key fact and I think equivalent characterization of modular lattices is what's called the diamond isomorphism theorem, which says that
what is the D for?
diamond. If you take the set of X that are between A intersect B and A, this is isomorphic as a partially ordered set to the set of X which are between B and A union B, where the maps between them are given by taking cup with B and cap with A. So this is a version in lattices of kind of one of the isomorphism theorems in group theory, so that the lattice of like subgroups. So in subgroup settings would be like the lattice of subgroups between H and H intersect K. So like H modulo H intersect K is going to be isomorphic to the lattice of subgroups between H times K and K, which is HK. Okay, so some kind of isomorphism theorem in group theory. Transplant to the setting of lattices. Another characterization of finite modular lattices is they have a version of Jordan-Holder theory. So every like maximal chain of like maximal increasing chain in the lattice has the same length. And so that gives you like a notion of like the size of an element is like the size of the maximal increasing chain. And the size of the maximal increasing chain behaves like the way you would expect under joins and meets and under unions and intersection, which is that the maximal increasing chain to a cup B plus the maximal increasing chain to a cap B is equal to the maximal increasing chain to A plus the maximal increasing chain to B. Yeah, so these are that's an equivalent characterization of a finite modular lattice, is if it has this notion of like the size of an element which satisfies that property. So I'm just giving different ways to think about the concept of modular lattice. It does all follow from what I said. So what we work with are categories where one, the quotients of each element form a finite modular lattice. Two, we want, as aforementioned, finite automorphism groups. And three, there's another finiteness condition. Which is kind of nasty to write down, but seems to be necessary for argument, and I don't want to worry about what it is, at least not right now.
It's like to control the function cell surjection from X to G, you need to know things like that the subgroups of G to the N, which maps surjectively to all factors, form a finite set. In the group case, in order to apply to reduce to prove that this is measurable for the sigma algebraic equation.
Kind of. So it is it is along those lines. It's not exactly that. So there's certain kinds of infiniteness which are fine. It just has to do with what's.
Your category do not have finite products.
Yeah. So I don't want to take my category to necessarily have finite products. So the union in this lattice is playing the role of a product. Whenever there is a product of A and B, then the union in this lattice will give you that product. But I do want to consider categories without a product. Yeah, okay, let me say that over here. So why? So why consider categories without products? So one example of this is one case that we're thinking about is fundamental groups of three manifolds. And fundamental groups of three manifolds are not just abstract groups. They come with an extra structure, which is the fundamental class of the three manifold lives in their third homology. And so to keep track of this structure, you might want to consider the category of oriented finite groups, which are pairs of G a finite group and S a class in the third group homology. And with morphisms, so morphisms from GSG to HSH are morphisms from G to H with F star SG is equal to SH. So this is a perfectly nice category. We might consider probability distributions on this category, but it doesn't have products, because if you take the product of two groups, you have different choices for the homology class you could put on the product, which are not determined by the homology of the two factors. But it does have greatest upper bounds least upper bounds and greatest lower bounds. And you can use the least upper bounds to do anything that you would want to do with products.
Does such things appear naturally in number-theoretic equations for Cohen-Lenstra?
Yes, they also appear. These will also, I mean, not this exact definition, but a closely related definition is going to appear in our work in number theory.
Is there something in these axiomatics which makes sure that every pro-object is isomorphic to one with like epimorphic transition map?
No. So what we just did is we just threw that into the definition of small. So what I'm going to so exactly, I'm going to define a small pro-object as one that is isomorphic to one with epimorphic transition maps, and so that it has finally many epimorphisms to every object. And so so if you can factor morphisms into a mono and an epi, and I don't remember whether we use the uniqueness of the factorization of the argument, then it's possible to check that this is equivalent to, well, first possible to check that everything can be expressed that way, or maybe you need to find it.
So you need this little bit more. As I said, the factorization is not just because of to prove categorically, for example, this factorization is unique, is you need a little bit more, either on the monomorphism or the epimorphism. And then no, I don't remember exactly, but then you can actually see that the project is like what we said before, but I don't remember now the precise formulation. But certainly, I remember that I looked at some examples where if you just use the monomorphism and epimorphism, you have cases with you have pathological cases where it's not.
Oh wait, maybe we should talk about it later to see. I mean, I don't think I don't think it's a counterexample to anything we stated in the paper. Maybe it suggests that we should do something slightly differently. I'm not sure exactly.
Sorry, can I ask, would you use roots of unity as an analog for your SGs for your fundamental classes in the number theory setting?
Well, okay, so not roots of unity exactly. Okay, so in number theory. Well, there's two answers to what the number theory analog is. One is that in the abelian case, you can look at my paper with Jacob Zimmerman and Mike Lebnowski, where we did a very explicit description of what extra structure you can put on the class group in the case of roots of unity. But another thing is was going to be in our upcoming work is you have a class in H3 of the group with coefficients in Z mod n, where n is the number of roots of unity in the base field. And so you see that such a class is well defined on the fundamental group of a number field using Art and Verdier duality. Maybe the one with split at all the real places, and so this seems to be the right invariant to consider, and it doesn't respect products in the way that you would want it to. And so we have these three assumptions, and then this is the setting in which we prove measures from moments. Theorem. And so to say more about what that theorem is and how we proved it, I first want to say that this is a set of generators for the sigma algebra, but it's not a very good one. It's not really a convenient set to work with, both when you're trying to prove things and when you're trying to extract information. And so a better idea is to look at a kind of canonical quotients of an object. And so like in okay, let me say first in the setting of like R modules. If you have R you have R like an Noetherian local ring. Noetherian ring with like finite residue fields. Or I mean, Noetherian local ring with finite residue fields. Oh yeah, residue field, yeah. If it's local, so there's only one residue field. Then small finite R mod or small pro-finite R modules are just the same thing as finitely generated complete R modules. So the
finitely generated R roof modules because they are not finitely generated over R. They are finitely generated over R roof, and then you don't need complete because they are automatically.
Okay. It's a very good point. Yeah, finitely generated modules over the completion of R is the more precise thing to say. Or finitely topologically generated complete modules, I guess. And then, so then the kind of the natural sets to consider are for S a finite quotient of R, and N a finite S module. You want to consider like U S comma N to be the set of all modules M such that M tensor over R with S is isomorphic to N. So these sets form a basis for the topology generated by the sets when we're just counting a surjection. I was just seeing if there is a surjection. These sets, it's obvious that these functions counting surjections are continuous because, if you fix any finite R module, it'll factor through some finite ring, and every surjection will factor through this tensor product. These sets are disjoint, right? You can write your space as a union of these disjoint sets for all finite N modules for each given S. And as S gets larger and larger, these sets will kind of refine and get you more and more information. These are kind of nice sets to work with. And so in the general case, what you want to work with is what we'll call a level, which is a set of objects of our category, which is closed under epimorphisms and closed under and unions, and is like finitely generated with those properties. Or the joint in the lattice. So if two quotients of G are in L, then their join in the lattice, their least upper bound in the lattice should be in the set L. And
so you allow something not there, and you take the join inside the bigger. In this sense, and it is just finitely generated relative to those operations.
Yes, exactly.
So you don't assume that it's finitely generated just under. It can be infinite. Infinite in many isomorphism classes. Of course, in the examples, it's finite. When you start with finitely many things, you get only finite.
No. Well, if you start with FP, you get any power of FP. by repeatedly applying the.
No, okay, it's countable and not, yeah.
Yeah. So in the examples, it is countable, but yeah, I mean it could be uncountable. In general. And so.
How can it be uncountable? Sorry, like if you just perform these operations, how do you get?
So you can have I could work with, instead of a Noetherian local ring, I could work with a ring in like uncountably many variables.
Yeah. Then you mean you have a lot of epimorphism, so that when you take the closure on the epimorphism.
Or yeah, well, sorry, not quite that. What I need is I want to work in a category where two objects can have uncountably many different joins. So basically, the similar thing to do is to do this, but instead of having one class in the third homology, have countably many classes in the third homology, and then you'll sometimes have uncountably many choices for the join. And yeah, and so that's why that choice is, that infiniteness is not at all problematic for what we're trying to do. The fact that there is, oh no, sorry, that infiniteness is problematic for what we're trying to do. So, and then so for if X is a pro object, you can define XL to be like the maximal quotient of X in L.
So you have to show it's. Okay. You prove in particular that this exists because once you take a set of generators, you take all the finitely many quotients of X which are one of those generators. Yeah, I'm not so sure. You have to think of it.
Well, yeah,
It exists following your axiom.
Yes. Okay. And so okay. Well, okay. Now let me say. I'll say very shortly what the third axiom is. So what are the natural sets to consider? You can then define for some G and L, we can define U L G is the set of X such that XL is isomorphic to G. And these are kind of the natural like basis for the topology we want to work with. And so okay. Yeah, okay, I'll say that now, and then I'll say. So the third condition is that for any of these, if you have any of these L, and you have an object in L, there should be finitely many objects mapping to G, so surjections K to G with K and L, and G is like a maximal non-trivial quotient of L, of K. Or maximal proper quotient of K. Or maximal, yeah, well, let's say maximal non-K quotient of K.
So you up to isomorphism.
Up to isomorphism, yeah. So we kind of don't care because we're going to look at the category kind of one level at the time, we don't care if the category is kind of very enormous, if it has many, many different elements, objects that all lie in different levels. But we do care if there are too many objects in a single level. Okay, so this, and so the way we care is we look at it kind of one step of the lattice at a time. So we use this notion of like the dimension function, the number of minimal steps to take in the lattice to get from one point to another. And what we need is that surjections which take one step in a lattice, there should only be finitely many of them within a given level.
And then you can prove that there is this, that the maximal quotient of x in L that exists under this third axiom. Is it?
Yeah, I think.
It looks like this is what you want to do.
Yes, yeah, and so yeah, I think it is. I think it's still with this axiom. I think it's still not obvious. I think you need to do an induction. You do an induction that involves the generating set of this level, okay. But it is a theorem. And so what? So the point I want to make with these levels is, so the theorem in our paper gives a formula for the measure of one of these sets. So when I say we construct the measure explicitly, we have an explicit formula for the measure in terms of these sets, in terms of the moments. And so that lets you answer a lot of practical questions about the measure. In particular, knowing which of these sets have positive measure and which ones don't tells you a lot about like the support of the measure, which is often an interesting thing to look at.
So now when you look at the, so in some sense we are using the idea of level to reduce the sigma algebra everything to those things of a given level.
Yeah.
And then for a given level, so if this things of a given level is a countable set, and of course the sigma algebra is all subsets. And
so this 3 does imply countability by an induction argument. It does imply that each level is countable because it implies it has finitely many. Or well, technically, okay, if there's a unique, if your category has a final object, or no, it's fine, because the level will have finitely many final objects in it. Yeah, it implies that each level is countable, and so so then the sigma algebra on each level is just the discrete sigma algebra, and so indeed, what we do in the paper is the vast majority of the work is done in a single level, or between finitely many levels. And so the actual measure theory doesn't appear. We're only considering functions on countable sets. And then there's some argument where you cite a general principle that says if you've constructed such and such thing at each finite step, then you actually get a measure in the sense of measure theory on the sigma algebra.
Okay, but it's just an abstract thing in measure theory. Such measures glue on to a measure on.
Yeah, there's some gluing statement about measures.
The measures will be solutions of infinite system of equations and non-negative numbers. Yeah.
Yes. Yeah, exactly. And so that's kind of a good perspective for how you should think about what's going on. So if you restrict, you restrict to a given level, what we what we have is we have an equation of the form, the sum over G in the level, the measure of the set of things whose level L quotient is G, times the number of surjections from G to H should equal the moment associated to H. And so this is a system of
H is in the level.
Yeah, for H and L, for all. And this system of equations, it's not just this set of infinitely many equations and infinitely many variables. Well, if you express it in terms of like an infinity by infinity matrix, it's like very naturally a square matrix. So the set we're summing over and the set of equations are in bijection because they're both parameterized by the level, by the same set. And so it's natural to write this. We can write at least heuristically.
Which finiteness conditions the measure you want? Like the measure of any point, the measure of everything should be finite, or does the measure of any point should be finite? Or?
So we're working in the setting where the moments are finite, and then, well, okay, at least if the category has a final object, which most categories we consider do, then the constant function 1 is a function of this form counting surjections. So that tells you the total measure should be finite. So I mean, essentially the total measure is finite. I mean, I think technically you can have infinitely many different pieces of your category with infinitely many different minimal objects, and each one gets its own measure. But yeah, I mean, essentially the total measure is finite. But even more, like all of these sums. Oh yeah, so in this countable setting, the total measure should be finite, and all of these sums should be finite, which could be a much more stringent condition than the total measure being finite. So, okay, let me make those more different. So you can make a vector whose entries are the MHs, a vector whose entries are the mu ULGs, and then a matrix whose like entry Aij is like the number of surjections from like Gi to Gj. If we order all the elements of L, which we can do because it's countable. And then the problem is essentially to find A inverse. Well, I mean, that's not quite the real problem. So if you want to find the inverse of A, it's not so hard to do because this matrix is like upper triangular. If you order the entries by increasing size, because there's only surjections from larger objects to smaller objects, this matrix will be upper triangular. And there's just a formula for the inverse of an upper triangular matrix that works equally well in the infinity by infinity setting. And so, well, like the theorem should be that mu is equal to A inverse M. The only problem with this is that the inverse of an infinity by infinity matrix doesn't always give you the inverse linear map, because the inverse linear map doesn't always exist, even when the matrix is upper triangular with non-zero entries on the diagonal. So there exists, from this system equation, there's like a formal solution that's obtained by inverting this matrix. And the actual difficulty is in checking when is this formal solution also an actual solution.
So I still have a question about the previous thing. It seems that I have a counterexample.
Okay.
You can rule it out. So just you had some axiomatic setup.
Yeah.
So I want to kind of oppose it in some way. So suppose you want to take a trivial example. You mentioned the final object may not be unique. So suppose I just take infinitely many many final objects which don't have to do anything with each other, no morphisms, and I don't need to introduce more things in the category. Just take those objects, and the morphisms are the empty set of different objects and one element for one object.
Okay.
Okay, then for a level, it's trivial. You take finitely many guys, and this is the level. But now, if you want a maximal, a pro-object, given by something else, lying another point, how could it have a quotient? You said it should have a maximal quotient in the level, but there cannot be a map to this, so you are stuck, so you have a problem there. You cannot map some other, you see, so it's another, so this shows that your axiom 3 was not formulated in such a way that it really implies the assertion that there is a maximal quotient in L.
Yeah, that's true. So it's either there's, so basically every object has a unique minimal quotient, and if the unique minimal quotient is in L, then it has a maximal quotient in L, and then otherwise it has not. It doesn't. Yeah. So yes. Okay.
Okay. So therefore you are saying that the measure is really okay. So this you then you can restate your thing in terms of this. Then you have there is some nasty measure theory problem. Like if you have an uncountable set and you have this sigma algebra, then it is not, a measure is not determined because the measure of the whole thing is not determined by the measure of the points. So somehow you.
Okay, that I will have to like think and like look at the paper and get back to you on exactly what we mean in that case.
Okay, just to make it clear, so A is matrix which has finitely many terms in each row, yeah?
Yeah, finitely many.
Yeah, so if given I, you get finitely many terms, yeah?
Or wait, is it finitely many on each column is the way I'm thinking about it. Or yeah, so this should be this should be flipped, the GJ.
I see. And mu, it's countable, yeah, unfortunately. Mu will be some non-negative vectors, yeah?
Exactly.
And M will be big one as, and the uniqueness, it's purely like monotonicity properties, yeah?
Yeah, so the uniqueness is relatively easy when this converges. So this sum may or may not converge. Like
but applying A to mu, you already need some conversions, yeah, because you get infinitely many things.
Exactly. So applying A, right? So applying A to mu, you need conversions to get M, but the problem is I give you M, and you have to tell me, does there exist a mu with this M? And so the measure that.
And why is the measure unique? Is it clear?
By monotonicity is positive numbers.
What?
It's by monotonicity, maybe kind of.
If this formula converges, okay. So I mean, okay. If it converges absolutely, then it's not hard. So how will we prove that mu is equal to A inverse M in the case of a finite dimensional matrix, given that M is equal to A mu? So the way that we would prove that is we would say, well, what is A inverse M is equal to A inverse times A mu, which is equal to A inverse A times mu, which is equal to identity mu, which is equal to mu. So for infinity by infinity matrices, every step of this argument works fine except for this one, associativity of matrix multiplication by vectors. So this is the step that needs to be checked. But if the sum defining A inverse M is absolutely convergent, if this is absolutely convergent, because the sum writing M as A mu is a sum of positive terms, the sum part of this matrix multiplication, we're summing non-negative terms, it follows that this sum is absolutely convergent. As in, like, for each entry of this vector, I look at all the terms which add up to one of those entries, and those sums, that sum is absolutely convergent, which means I can freely rearrange it. And if I can rearrange the sum, it's very easy to prove associativity of matrix multiplication. So to make that a useful criterion, you need to calculate the A inverse. And it turns out we can calculate A inverse using the Mobius function of the Poe set of quotients. And then so there's like a relatively simple formula. So what that formula ends up being is a form of inclusion-exclusion. If you're interested in the measure of this set G, what are the things whose largest quotient in L is equal to G? You have to take first, count surjections onto G, everything with a surjection onto G. And then you have to subtract off things with a surjection onto something that is a little bit larger than G. Surjection is something, a larger object in G that surjects onto G and is still level L. And then you have to add back in things with like a length 2 surjection onto G, and so on. You kind of have an inclusion-exclusion. An inclusion-exclusion formula. And if that inclusion-exclusion converges, absolutely, then it must give you the correct formula. So that if there is a measure, it must be given by that formula. So in particular, if the inclusion-exclusion converges to something negative, there can't be a measure. If it converges to something which is not positive. But if it converges to something that is positive, it still might not be a measure, because it's not as simple to do this associativity argument the other way and prove that mu equals A inverse M actually is a solution. But what we check is, as long as that function converges like sufficiently rapidly, if it converges when you put a little bit of an extra weight function in, then you can do the other kind of, you can show that the measure really exists.
Can you say more about this inclusion-exclusion formula you get from Mobius functions?
Yeah, so if you have well, let me say something first in groups. So so the statement is something like if you have like x a profinite group, then the function that is 1 if the maximal level L quotient of x is isomorphic to G, and 0 if the maximal L level quotient is not isomorphic to G, is given by, first you count the surjections from x onto G, and you want to get 1 if x actually is G, so you divide by the number of automorphisms of G. And then you subtract off some multiple of the number of surjections from x up to like G prime, where like G prime is a surjection onto G, whose kernel is a simple G prime group. So the simplest kinds of surjections of groups are the ones whose kernel is a G prime invariant subgroup, but it doesn't contain any further normal subgroups in between the kernel and the trivial group. I don't remember exactly what the weight functions go to in this setting, and then you would end up adding back in with some weight surjections of x to well, in this case, you'd be interested to fiber products over G of 2 of these groups where the mapping to G with kernel simple. So making the kernel product of 2 of these simple things. And so in general, the only terms that appear in the sum are groups which are mapping to G, and the kernel is semi-simple, is a product of finite simple G groups. Or not G groups, but finite simple.
No, but suppose, because if something maps to both G prime and another one, then by Gauss it maps to the surjectively to the.
Yeah, yeah, exactly. Yeah. Yeah. So we're only considering.
Okay, thanks. Like it's an idea. I just wanted an idea.
Yeah. And so the fact that you only need to consider the semi-simple like morphisms here, the morphism whose kernel is semi-simple, is a property. It's like a vanishing property for this inverse matrix, a vanishing property for this Mobius function, which is very helpful in the argument in like bounding what you need to consider when you're checking. You can rearrange these sums.
This it will come from the fact there's a finite number of quotient behind any group. Because I feel like if there could be a quotient, a group where it has an infinity of quotient and no maximal quotient, it would like break everything. But I guess it's impossible because you have finite.
Yeah, all the objects of our category will have finitely many quotients. And of course, for finite groups, that's true. Okay, so I might say more about that, but I first want to say what I, in fact, should have said before, which is I gave some axioms, but like in concrete terms, to which categories does this apply? So the three big ones, the most familiar ones that I also expect to be the most kind of relevant for different applications, is you can look at finite groups, finite rings, and finite modules for a fixed ring R. And if you do that, and so then in these three cases, your measures we're studying would be measures on profinite groups, profinite rings, and profinite modules. Profinite rings and profinite modules are somewhat strange, or are less commonly used concepts than profinite groups, but they each contain, contain more familiar things, right? So as I mentioned, a small profinite module is the same thing as a finally generated module for at least if you're over a complete Noetherian local ring. And small profinite rings will certainly include the complete Noetherian local rings with finite residue field.
Are rings commutative?
So it works for both. So when I'm talking about local rings, I'll be talking about commutative rings, but it also works with non-commutative rings, and in particular when you're considering modules in some of the number theory cases, it's certainly convenient to consider modules for non-commutative rings. And so a generalization of this is you can consider finite algebras for a Maltsev variety with operations of finitely many arities. So what is a Maltsev variety? A Maltsev variety is a variety in universal algebra, which means it's a collection of operations that might take some number of elements of a set to a single element of a set, and a bunch of equations those operations satisfy. And Maltsev varieties are the special case where you can define an operation T, which satisfies the following weird identity, that T of x, x, y is equal to y is equal to T of y, x, x. So it's a function of three things, that the first one cancels the second one, and the third one also cancels the second one. So the example would be, groups are a Maltsev variety because you can take T of x, y, z is equal to x, x, y inverse z. So most varieties in universal algebra would have finitely many different operations, and that's OK for us, but it would also be OK if you have infinitely many different operations, as long as they're not infinitely many unbounded arity operations. If you have infinitely many binary operations, that's fine, as long as you don't have ternary and quaternary and so on. you can look at the list of Maltsev varieties and get many examples where this theorem applies. In particular, groups, rings, and modules can all be expressed in this way.
So all those get model lattices?
Yeah, these all get model lattices, and I mean,
because of this property.
Yeah, so it's a theorem in lattice theory. So for groups, rings, and modules, the quotients of an object are parameterized by subsets of the object. We have normal, subgroups, ideals, and submodules. But for a general variety universal algebra, the quotients are not always parameterized by subsets, but they are parameterized by equivalence relations. So there's a bunch of equivalence relations that give you quotients, which are called congruences. And an equivalent characterization of Maltsev varieties is that the congruences commute with each other. And so there's congruences are like equivalence relations that give you quotients. So congruences in universal algebra are equivalence relations on the set, which are kind of compatible with all the operations of the algebra. So if you apply the operation to equivalent elements, you'll get equivalent elements out. Compatible with the operations. And so the reasonable definition of Maltsev varieties, I mean, it's completely unclear why you would care about this, but the equivalent characterization, if and only if the congruences commute, in the sense that if you have two of these congruences, like there exists B such that A is equivalent by the first congruence to B, which is equivalent by the second congruence to C, if and only if there exists B, I don't know, D, such that A is equivalent by the second congruence to D and equivalent by the first congruence to B.
So this is a property of
any two congruences.
Yes, and then this condition on all possible congruences.
That it will imply the modular lattice condition.
So this is an extra condition on the Maltsev variety.
This is equivalent. So there's an equivalence between being a Maltsev variety and this condition. So there's two equivalent definitions of a Maltsev variety.
You say a Maltsev variety.
It has this identity.
Its operations, and so that it is the
ternary operation.
What?
There is a ternary operation.
Yeah. So there's a theorem that there exists a ternary operation with this satisfying this identity, if and only if all. I think it's Maltsev's, and that's why it's called the Maltsev variety.
Yeah. A Maltsev variety is operation. Okay. A Maltsev variety means that you have like consider some algebras that have a certain type of operation satisfying certain identities.
Yeah, and then using those operations, you can define one which satisfies this particular identity.
Okay. Okay. So if you can, okay. There is a notion of variety. Okay. The reason notion of variety without without the Maltsev condition.
Yeah.
The Maltsev condition says that there is an operation that you can express in terms of the previous.
Yeah.
What does it mean express? That's by a formula?
By a formula, yeah.
By a closed formula.
Yeah, closed formula, yeah. And which satisfies this. And what that means, so that means the equivalence relation commutes, and I mean it's it's not hard to prove that these equivalence relations commute with each other using this, because you would just take D to be T of A comma B comma C. And then this commutativity property, you can see it gives you the modular lattice. You can check, it gives you the lattice condition. Like, so in particular, the fact that this is true means that we can combine these two equivalence relations in a well-defined, to give a nice equivalence relation between A and C, where A and C are equivalent if there exists such a B. And that gives us the least upper bound, or in the lattice of quotients.
Oh, you get intersection of this guy.
Yeah, and you can take intersections. Yeah, so then you can check the modular lattice property from this, and so all you need to check is the existence of this operation, and because this operation you can get it from the group law, all you need to check is the existence of a group law. So anything, the key example is like any kind of group with extra structure. If the extra structure can be expressed as extra with extra operations, any kind of group with extra operations that will come from a Maltsev variety, because you can always use the group law to find this Maltsev operation. So that explains why rings and modules appear, because those are both grouped with extra structure. And then other things which are grouped with extra operations, like Lie algebras and Jordan algebras, will also appear. So I have no idea if it's ever a good idea to study like measures on pro-finite Lie algebras, but if it is, like, we're ready, and we have a theorem that applies to that case. And then even more exotic things. So if you just look up Maltsev varieties, then notions like semigroups. So groups without associativity, you can still do this using a slightly more complicated formula.
Oh, by the way, you consider measures values in real numbers, but when we consider it like additive monoids, so K0 varieties.
Wait, you're changing what my measure is valued in now?
Values, yeah. When we have continuous parameters, you don't count, but consider it like whole variety of quotients with some algebraic variety. And yeah.
I didn't think at all about generalizing in that direction. I'm
Instead of geometric examples, then the quotients will be usually replaced by some algebraic varieties, yeah?
Oh, so you're saying, okay, I see what you're saying. You're saying that let's consider categories where the set of quotients is no longer a finite set, but it is a variety of finite type. And you're saying, let us do everything here in K0 of varieties.
Yeah, and this positive part, yeah. So.
Reminds me of this theory I heard of called motivic integration.
Yes.
So I obviously do not know off the top of my head if what kind of additional assumptions, finiteness assumptions you would need, or other kind of assumptions you would need to make the argument run in the setting of K0 varieties. In particular, the results we use about this Mobius function, the vanishing we prove or no, not we prove, but the vanishing we quote for this Mobius function. Like, I would worry that vanishing doesn't necessarily hold in K0 varieties, but only holds in, some for some motivic measures, kind of thing. Yeah, maybe that's fine.
If you consider things like, I don't know, semi-group, let us say, or monoids, I don't know what this thing, anyway, let us say without inverse. Sometimes they consider things without inverse. which is called a semi-group. Sometimes semi-group is like depends on the reference. But let us say monoid, let us say commutative monoid, like in toric geometry. So there is a notion of equivalence relation that allows you to define quotient monoids. On the other, is this a Maltsev?
I think that it's not a Maltsev variety because there's no way you could ever cancel. So there's no way, like, you couldn't define any operation which uses x in a non-trivial way, where like a function of x and y in a monoid which uses x in a non-trivial way, which takes the value y. Like, because like you could have a monoid. I mean, okay, you consider the multiplicative. Maybe the right thing to say is you consider the multiplicative monoid of the field F2, which is two elements 0 and 1. So, like.
Yeah. So no. Okay.
Like if x is 0 and y is 1, this has to be 1. So x can't appear in the formula at all, and so it can't. And so, but then if like the first term can't appear in the formula, then it contradicts.
So probably the quotients do not form a modular lattice in the case of monoids, commutative monoids.
Yeah, I think that's correct. But somehow it is okay if you get rid of associativity, but only allow, and you get rid of the identity, but always, as long as you allow left and right division. So if a left and right division exists, then that's okay for Maltsev varieties.
Left and right division without associativity?
Yes.
And so this is x, y, inverse z depends.
No, yeah. So it's a more complicated formula than this. I don't remember off the top of my head. It's like you use each element multiple times, and then you divide something by itself, and then divide something else by that. It's like some more complicated formula, but somebody checked it. And then maybe most interestingly, I'm not sure. So hating algebras are a Maltsev variety. So hating algebras are models of logic without the law of the excluded middle. So they're like Boolean algebras, but kind of without the rule that like A or not A is always equal to true. So A may not equal not A. And hating algebras form a Maltsev variety, and so you can get a notion of a random hating algebra. For example, you can study measures on spaces of pro-finite hating algebras. And then you can take these things and you can put on them other kinds of extra structure which don't come from operations in universal algebra, in particular these kind of homology classes, any kind of extra structure which, yeah, if you have this notion of push forward for the structure, then you can do that.
So this modularity will automatically follows.
Yes. Yes. So you can check that this. In fact, if you define morphisms like this, it preserves the lattice of quotients. It preserves the lattice of quotients. Yeah. And we check some other kind of stability properties of that form for this class of categories.
Actually, I had another example of model lattice of different nature. You consider like Arakelov lattices, yeah, yes, and consider semi-stable with given slope.
Okay.
Then you get modular properties as well, yeah.
With what partial order?
One is for a given slope, we have kind of sublattices with a given slope, and the quotient again. So we get natural.
I see. Yeah, I don't know if that. Yeah, it'd be interesting if there's a category where that is the surjections. Yeah, so let me say something brief about how like what are the kind of the key ideas in the most analytically difficult parts of it. So we have a level that's generated by a finite set of objects, and like observe, you can always take that finite set of objects to be closed under quotients. So you can assume your level is generated by a finite set of objects that's closed under quotients. And then each object has a dimension, which is like the length of a maximal increasing sequence in its lattice. So if you take L generated by a finite set, stable under quotients, and then you can take like Ln, which is generated by all generators of L, of dimension less than or equal to n. So for finite groups, this would be the number of terms in the Jordan-Holder filtration of the finite group should be less than or equal to n.
Ln generated in the sense?
In the same sense, yeah.
No, but for large n, this is equal to L, yes?
Yes. For large n, it's equal to L. For n equals 0, it's very small and just consists of some minimal objects. And so the point of this is this lets you interpolate between some very small thing that you understand and the L that you want to understand. And the point of the difficult arguments, which is to showing the existence and also checking that the limit of the moment is the moment of the limit, both of those require an induction on n. And so starting at L0 and then going to L1 and then going to L2 and then going up to Ln.
Oh, sorry, I just got lost. You have this general theory of measures, yeah? But then in concrete case you get kind of concrete prediction to like Cohen-Lenstra statistics.
Yes.
And you should produce it from something, from nothing or from a level of...
I mean from moments. So the whole point...
How you get moment, you should invent formula for moments? Or?
Yes, okay. So actually let me talk about that now, because that's what that's the other thing that I wanted to talk about today. So where are the moment formulas coming? So I summarize this and let me say in kind of more detail. So where do moment formulas come from? And so the setting we had is if you have a cover, DC is a cover of curves with Galois group gamma. And H is a finite gamma group. And maybe we take the order of H and the order of gamma to be coprime. Then surjections of gamma groups from pi1 of D to H are in bijection with covers H covers of D, which are in bijection with H semi-direct gamma covers of C, where the H covers here we're taking them to be unramified, and the H semi-direct gamma covers we're taking to have all their ramification lie inside gamma.
And you want that the gamma cover of the semi-direct product gamma cover is the given one.
Yeah, oh, sorry, yeah. H, yeah. Whose gamma cover? Whose gamma cover is T? And then when we...
You have maybe some automorphisms, I don't know, some automorphisms of the situation that...
Yeah, so...
In different ways, so when you count things, it's kind of not...
Yeah, so it turns out to be convenient to count these things together with a fixed point in the fiber over infinity, which will kill all the automorphisms and will make the stacky counts into regular counts.
But the second formulation is kind of ugly because it covers ramified for gamma and not ramified for H yet.
It's not that bad. So in number theory, you're always wanting to put some condition on the branching of a cover. And this is, yeah, so, so the point is, so what's the point is calculating moments. Should be the same as counting these covers. H semi-direct gamma covers of C, which should be the same as counting FQ points. Of some moduli space. And so you can define a moduli space of covers for any finite group and for any local condition on the branching of those covers. And so this is a specific class of finite groups and a specific class of local conditions that's relevant here, and that makes some calculations easier to do, but eventually one will want to do this for all finite groups and all local conditions.
But this space will be a zero-dimensional scheme, yeah? Because you fix already verification points for...
No, because when we're doing moments, we're summing over the d's, so we are dropping the second condition. And we're not fixing the ramification points. We're just fixing maybe the number of ramification points. So which is fixed number of ramification points, let's say. And we might as well take C as P1 for simplicity. So we're considering these moduli spaces, and this is called the Hurwitz space, that are moduli spaces parameterizing covers of P1, curves mapping to P1 with a given Galois group with a fixed number of branch points and some restriction on the ramification of the branch points. And to count them, to count these moments means to count these points. So we know what we need to do is to calculate the cohomology of the Hurwitz space. Of the Hurwitz space. And one thing is really nice about these cohomology groups. These are the same over Fp and over the complex numbers. So there is a natural isomorphism between the cohomology of the Hurwitz space in characteristic 0 and characteristic P, as long as P does not divide the order of any of the finite groups in the picture. And so the reason for this is the Hurwitz spaces have some compactification by a stack where the complement is a smooth normal crossing divisor. And then you can use that compactification to compare the cohomology in characteristic 0 and characteristic P. Or rather, the configuration space. The ramification locus is n points in P1, and you compactify the space of tuples of n points in P1. And so this kind of reduces, to the problem of calculating the cohomology in a topological setting of the space parameterizing branch covers of the complex projective line at some number of points. So it suffices to calculate, like in the topological setting. You have to know for me. So the theory, right? So it almost suffices. And so the theory is that if you could calculate the cohomology in the topological setting, you would recognize all the cohomology classes as explicit classes you can write down, and then you could write them down in characteristic P and see how Frobenius acts on them. So for most finite groups, we in fact run into trouble earlier that we don't know how to calculate the cohomology of the Hurwitz space well enough. Only over the complex numbers.
When you can calculate it, is it always just tape twists you see, or is it?
Well, there's finite. There's finite. So the I think maybe in low degrees it can be ardentated. It certainly shouldn't be ardentate in every degree, but in low ordinary degrees or high compactly supported degrees, I think it is. So, but yeah, because this space is smooth, the ordinary cohomology in low degrees is the same as the compactly supported cohomology in high degrees. And so it's equivalent to think of them, of either of those. And so in particular, the first case that we consider is like H0. Okay. Let's write down here. So the first case of interest is equal to H0, which is the same thing as counting components of Hurwitz space. And so already in this case, you see that there can be a non-trivial Galois action. So there's a certain set of components that make sense over an algebraically closed field of any characteristic, but Frobenius will permute those components in a non-trivial way in characteristic P. So what do we do when we can't compute the full cohomology is we just count the components. That lets us compute points in the Q to infinity limit, and then we hope that this gives us the right answer for a fixed Q as well.
So you count the components, but without knowing the Frobenius action?
Right. So what you do is you find an explicit invariant separating the components. So what is that invariant? So if I have, well, what I say is in this case, if I have a cohomology class in the second group cohomology of H that is gamma invariant, I could integrate that class over the cover D and obtain a number. And that integral is constant on every component of this moduli space. So this invariant on every geometric component. So this gives me an invariant that separates the geometric component. And then to calculate the Galois action on the components, I then need to calculate the Galois action on this invariant, which I can do using the Galois action in cohomology.
But of course here there is no Galois. If there is no Galois, that Galois is trivial.
Well, I'm saying you can define that invariant. So you can define this invariant kind of uniformly over any base of the complex numbers of the finite field. You can show this invariant is a complete invariant of the component over the complex numbers as long as you have sufficiently many ramification points. There's a sufficient ramification condition, which is unfortunately ineffective, I think. But as long as you have enough ramification points, this invariant is the only invariant distinguishing components. And then you can conclude that this same invariant in characteristic P is the only invariant distinguishing components in characteristic P. But now in characteristic P, we can calculate the Frobenius action on this invariant, and therefore get the Frobenius action on components.
Why is the Frobenius can act non-trivially if you have a cohomology class? Because
it acts non-trivially on the integration map. So the integration in characteristic P is from H2 of x. Well, also here, ZP goes to like ZP of -1, something like this. Yeah, there's a cyclotomic action, and so it ends up depending on the congruence class of the size of the finite field, because the action is always via the cyclotomic character. So actually, okay, I should say something about the history of this. So this strategy is for using these Hurwitz spaces to prove cases of Cohen-Lenstra is due, I think, to Ellenberg, Venkatesh, and Westerland, and they were able to calculate the components and bound the cohomology in higher degrees in a special case. So if like gamma is specifically Z mod 2 and H is odd, of odd order, that's like the main case that they studied. And the headline results in their paper are in the case where H is an odd abelian group specifically. And then they didn't do all the component, well, and then their ideas were also crucial for the component calculations that are needed in the general cases. But like defining properly this invariant, they also figured out how to do. And so so there are more. So I just wanted to kind of sketch this. Are there more questions?
Yeah, so I think this explains how we get ideas for Cohen-Lenstra statistics in functional field case, but in number theory case, is it some?
Right, okay, so so what do you end up doing? You're counting components, and that gives you a formula. And your formula ends up being pretty simple formulas for the moments. And the idea is that the formulas are simple enough that you can guess that the analogous formula holds in the number field case. And so definitely the simpler the formula is, I think the more convincing it is that you're doing the analogy correctly. And so that's one advantage of working with moments and working with this notion of moments specifically.
Because as I remember vaguely, this original Cohen-Lenstra statistic considered huge integer matrix with random coefficients, and consider quotient by the lattice and consider P part of this.
Yeah. And so that ends up being an equivalent description of the measure. And so actually, in our methods have already been helpful for people working in questions purely of p-adic random matrix theory. If you want to calculate the distribution of the co-kernel of a p-adic random matrix, which is coming maybe not from uniform entries but from some other constructions, then it can be convenient to do it by first calculating the moments and then applying our theorem to turn the moments into the measure. In Cohen-Lenstra theory, they were originally using p-adic random matrices to try to get a handle on this probability distribution. But our techniques are kind of powerful enough that they can help with purely p-adic random matrix theory questions.
So I think there was a Bourbaki talk on something like this in 2019 I remember about your name and all the spaces were mentioned. Is it?
I think you're getting. I think you're getting different. Wait, is there? So was it maybe the work of Melanie with Yuan and David? There was a Bourbaki on that.
There was something about Hurwitz spaces and Cohen-Lenstra was mentioned.
So I know there was a seminar Bourbaki on the original work of Ellenberg, Venkatesh, and Westerlund. And so that one certainly. I don't think my name would have been mentioned in that talk because I don't think I had done anything relevant by then.
Okay, maybe I.
But I don't know if there might have been a seminar Bourbaki on this paper of Melanie, David, and Yuan, and I think I would have been mentioned in that one because I figured out a simpler
There was a more recent one where you mentioned, but I think that there was one before COVID that was also with some. Okay, but maybe it's. Okay.
Yeah, I don't remember. We can discuss. And so. The last thing that I want to talk about is the application to three manifolds. Well, I'll put in quotes application to three manifolds, or the application of the same ideas to three manifolds. Which is also due by myself and Melanie. And we had, so it's not literally an application of our main theorem, but it's an application of the same kind of ideas. To the limiting distribution, we calculate the limiting distribution of the pro-finite fundamental group of a random three manifold. So the notion of a random three manifold we used was defined by Dunfield and Thurston, who said, well, it's classical. You can make an arbitrary three manifold by Heegert splitting, by gluing together two handle bodies, or it's better to think of it as two copies of the same handle body, where a handle body is a ball with G handles, G cylinders glued to it, and its boundary is a Riemann surface. So the boundary of the handle body is the Riemann surface sigma G. And so what data do you need to glue together two copies of your handle body? You need an isomorphism. An isomorphism from sigma G to sigma G. So if you have a map from sigma G to sigma G, you can use that to glue together two copies of the handle body, and you get a three manifold. And then the map only depends the three-manifold you get only depends on this map up to isotopy. It depends on the mapping class. So it lives in the mapping class group of sigma g. And so a random three-manifold is going to come from a random element of the mapping class group. How do you make a random element of a group? You just take some generators. You take a random long word in those generators. Maybe make sure the identity is in your generating set. And then you consider the limit, where first the length of the generator's generating set goes to infinity, and then the genus goes to infinity. And that's a very natural limit to take that gives you a very reasonable model of random three-manifolds.
It doesn't depend on the choice of
Yeah, so the measure on three, or well, it's not really measure. So yeah, the distributions on three-manifolds you get might depend on the choice of generating set, but the pro-finite fundamental group distribution is independent of the choice of generating set.
And any three-manifold comes from this.
Yeah, so any three-manifold comes from a Hilgard splitting, and so it comes from this distribution for certain values of g and analog.
compact, smooth.
Yeah, compact or oriented three-manifolds. So yeah, we're working with oriented three-manifolds, although a version of our method would certainly apply to unoriented three-manifolds as well. Yeah, so yeah, we're working with closed oriented three-manifolds, so compact, boundaryless three-manifolds.
And they should have really well-defined profinite things with definitely many homomorphisms to given finite group.
Well, they're compact, so the fundamental group is finitely generated. So they're certainly.
No, for given manifold, yes, but if you make it random, very big guy, it will have really finitely.
Yeah. So I mean, in fact, this kind of follows from the work of Dunfield and Thurston. What they calculated is the expected number of surjections from the fundamental group of this three-manifold to a fixed finite group, and this expectation is bounded as a function of g, and in fact converges as g goes to infinity. So yeah, on average, the number of surjections from a fundamental group of random three-manifold to a given finite group is bounded, even though it can get arbitrarily large. It's bounded on average, which is kind of the boundedness that's relevant for us. So because they calculated the moments for us, we basically had to apply our theory to get the measure from the moments. It's a little bit more complicated because we wanted the moments with extra structure, so we had to calculate first the moments with some extra structure of this fundamental class. But most of the kind of topology in our paper is in the paper of Dunfield and Thurston, and what we're doing is like applying kind of algebraic and analytic techniques to better evaluate this measure. And so using this, we can answer certain kinds of existential questions about three-manifolds. So questions, does there exist a three-manifold with a certain property? Because for properties of the fundamental group that depend only on the small finite quotients, often the easiest way to find a three-manifold with that property is to show that a random three-manifold has that property with positive probability. So an example of the kind of thing we can do, if you consider like the set of like pi1 profinite fundamental groups of three-manifolds inside a set of all profinite groups, you can take the closure in this topology. So you can look at profinite groups which are well approximated by three-manifold groups. If you only look at the first million finite quotients of your profinite group, you can't distinguish it from a three-manifold group. And so a question you could ask is, what is the set the closure intersect with a set of finite groups. So what are the finite groups that you can't distinguish from three-manifold groups by looking at only the finite quotients of the three-manifold? And so, well, it certainly contains all finite three-manifold groups, all finite groups of three-manifolds, because they certainly will lie in both of these sets. And it contains exactly one more family of groups whose smallest member has 120 elements and is some kind of semi-direct product of Z mod 15 with the 8-element quaternion groups. So if you take the semi-direct product of the maximally non-trivial action of the 8-element quaternion group on Z mod 15, that will not come from any three-manifold itself by Perelman's theorem, but it is very well approximated by the fundamental groups of three-manifolds.
What is Perelman's theorem? Question the one about Poincare.
Well, the geometrization. I mean, it's not.
Z
mod 15. The 8-element quaternion group.
Is there some natural kind of, like hyperbolic manifolds, this fundamental group kind of close to this guy?
I have no idea if there's a natural way of writing down such hyperbolic manifolds. So our theorem certainly implies that there does exist a sequence of hyperbolic manifolds whose fundamental group is close to this guy, because almost all these three manifolds are hyperbolic. So our construction produces plenty of hyperbolic manifolds. But I don't know if there's any kind of explicit way of writing them down. And I hope there isn't. And I hope that our theorem is the best way to find these. But it also would be cool if there was some nice explicit construction.
So the 8-element quaternion group is a Booleanization, which is it is just the one in the usual quaternions, plus minus I plus minus j. So how did it act on Z mod 15?
So the abelianization is Z mod 2 times Z mod 2. And any faithful action of Z mod 2 by Z mod 2 on Z mod 15 works. So there's Z mod, so you can think of, okay, Z mod 15 is Z mod 3 times Z mod 5. And I want one of the Z mod 2s to act non-trivially on Z mod 3 and the other one to act non-trivially on Z mod 5. Okay, let me say, the general member of the family, you can take Z mod A times Z mod B times Z mod C times Z mod D, whole thing semi-direct product Q8, where A, B, C, D are odd and relatively prime. And you can have the quaternion group act on these four cyclic groups by its four characters with plus or minus 1 value. So this can be trivial character, and then the three non-trivial plus or minus 1 value characters give the actions on these three. And if one of these, if two of these three are trivial, then it comes from a three-manifold. It will be a subgroup of SO4. But if two of them are not trivial, then it doesn't come from a three-manifold, but it's still well approximated by three-manifolds.
If at least two of them are trivial.
Yeah, two of the first three. If two of the first three are trivial, then it's a three-manifold group. It will be a central extension of a dihedral group. So the interesting ones for us are the ones where two of the first three are non-trivial.
Then it is not. And for a three-manifold group, is it residually finite or unnecessary?
That is a theorem. So yes, three-manifold groups are residually finite. So yeah, you can't. And so the pro-finite completion is really not losing information about the three-manifold group.
What about on the level of conjugacy classes?
I'm not sure what you mean.
Or like conjugacy classes in Taiwan mapping to conjugacy classes in the profinite completion. I think a priori it's a different question.
Yeah. Okay, so yeah. So I mean, the thing that's true is. Oh no, you're right. Yeah. So right. No. So yeah. You can lose information, right? So the map. So there's some information you can't lose. So the map from pi1m to pi1 hat m is always injective. Yeah. But it's not necessarily the case that two three manifolds with the same profinite fundamental group have the same ordinary fundamental group. But like finiteness, for example, is an invariant that is preserved by passing through profinite completion in residually finite groups. So this existence result is not because there is a single three manifold whose fundamental group is infinite, but for which this group is the maximal finite quotient. It must be a kind of sequence of three manifolds, of each with infinite fundamental group, but with fewer and fewer finite quotients of bounded size.
Yes, story works for three orbifolds.
So.
No, not stacks again. It seems like we moved on from this.
So I would certainly expect that something similar to what we did can be done with orbifolds. You first have to decide what kinds of orbifolds you allow. Like, you could have orbifolds that only have, like, I don't know, something natural from the point of view of like number theories. You consider orbifolds which only have orbifold structure on curves in the three manifold, and then you would need to pick a random model for how you make them. So maybe we're going to do handle bodies with lines inside the handle body, and we're going to glue them by a mapping class group of the surface with marked points.
Because I think generalization actually works also for orbifolds. It should work, yeah.
Oh yeah. But there should be more orbifolds with finite. Yeah, there's many more orbifolds with finite fundamental group than.
Since the fundamental group, you said it's residually finite, so it suggests that an orbifold really should have a finite tile cover, which is without. It should be a quotient of. Is it the case in these three manifolds?
Oh, you say that every orbifold has.
Is a quotient of a usual manifold.
Well, that's not true for surfaces, so I don't think it would be true for three manifolds. Okay, I mean, my lecture is done because we're out of time, but feel free if someone has more questions.
So in the last example, you really kind of know all moments explicitly. How we get it?
Yeah. So what we have, right? So what we have in our paper is a calculation of moments, and from the moments you calculate a measure, and then from the measure you look at the support, because you have a formula for the measure using these open sets that's a product formula. If you do it with this extra structure, it's a product formula. And so you can give precise, necessary, and sufficient conditions for the measure to be positive. And then for all those conditions, you go back and check that they hold not just with probability 1, but they hold actually for the fundamental groups of three manifolds. And so that then gives you that necessary and sufficient conditions for a three manifold to exist of certain types. So, but the moments which are necessary for this theorem is not just this group itself, but it's every group mapping to this one where the kernel is semi-simple. So it's quite a lot of groups that are kind of relevant to check that theorem.
Use classification of simple groups, maybe no.
Yeah, you don't use it in a fundamental way. There's certain there's certain catchy statements in our paper that depend on the classification, but the actual chunk of the main theorem doesn't. Because basically, only finitely many simple groups are relevant at one time, because you're only considering one level at a time. There's finitely many finite simple groups in the level. And we don't need anything about finite and simple groups other than that there's only finitely many of them to worry about at once. Okay, if there's more questions, then maybe we can talk about them at T, because people probably want to know T.